Good morning. Thank you for hanging around on Sunday late. I'm going to talk about mathematics of color addition games. So this talk was inspired by a mathematical color addition game called Al-Jabar, a game of mathematical strategy that was developed by Robert Schneider, who was a PhD student of Ken Ono at Emory University. He developed this game to play with his son Max. There's Robert on the left playing the game, and there's Robert on the right with Max. Riding a train. They like trains, I guess. The rules were first published in 2011 in conjunction with the Celebration of Mind here in Atlanta. And then in 2012, Robert gave a talk at the Kentucky MAA section meeting and shared the rules with me. And then since then, I've been using them in class and thinking about different ways to interpret the mathematical structure of the color addition rules. So we'll start with the way Robert thought about this. And he thought about, well, we'll start with the rules first. So it's a mashup of additive and subtractive color mixing. So subtractive color mixing is like mixing pigments. Additive is like mixing light. So we're going to sort of mix our metaphors here and throw in some other stuff. So the subtractive rules are what you think of with playing with finger paints. Right? Red plus yellow is orange, blue plus red is purple, and yellow plus blue is green, just like you've always done when you're a kid. The next rule is the additive one, and we're going to sort of mix our metaphors here and continue using red, yellow, blue as our primary colors rather than red, green, and blue on the computer screen. And so white light's sum of all colors, so red plus yellow plus blue becomes white. And then the last rule is this sort of binary thing that it's like flipping a switch. If you flip the red light switch, you get red light. Flip it again, lights go off, you get dark. We're going to symbolize that as the black piece. Okay, and there's a game of Al-Jabar. That's Carolyn Yakel's third appearance today. Those are her elbows there. So Robert originally thought of this as a group structure, Z2 cross Z2 cross Z2 with some colors. And here's a relationship between the 8 colors and the elements of the group. So we see that black becomes the identity, and white is the sum of sort of all the primary colors. And this gives us some interesting color addition rules that don't arise out of using finger paints, such that purple plus orange is green. Let's see if we can get this little thing out of the way here. That will not go away. Oh well. You can still see. Oh. Whoa. You can still see the green, right? Okay, so I thought about this a little more geometrically after I was playing a game with Robert. This was Robert's original logo of Al-Jabar, a Venn diagram, seeing where all the colors overlap. And it occurred to me that you could put a Fano plane in there nicely, sort of upside down triangle shape of a Fano plane. If you don't know what that is, that's a 7-point geometry with 7 lines. We'll talk more about that in a second. And based on that observation, Robert decided to change the logo of his game. So now it's this Venn diagram of the Fano plane on the right. But I think if you just color the Fano plane, you could recover everything without the surrounding circles. So here's the colored Fano plane. So we have 7 lines. The edges of the triangles, the diagonals, and the circles align in the geometry, which is a weird kind of thing if you're not used to such things. But the idea there is that the sum of any 2 colors on a line is the third color. We don't have the black piece in there, but we can recover that by thinking about the sum of any of the 3 colors on a line becomes black. Because sum of 2 is 1, add that back in, you get black. Okay, happy coincidence, let's suppose that. In the fall of 2004, I started writing a book about proof, which was published this last fall, and had that Fano plane on the cover, and 2017 minus 2004 is 13. That's a long time to write a book, and that's a stretch to get 13 in there, but I got it. So there we go. Quick bit of graph theory about this. So you can talk about vertex coloring of a graph, so no 2 vertices that are connected by an edge can have the same color. Edge coloring, no 2 incident edges can share the same color. And with a total coloring, you want to put those together and also include the fact that no vertex can share the same color as an edge that meets that vertex. So here's a coloring of K7, which we'll look at on the second page. And what we'll see here is that the edge color becomes the sum of the 2 vertex colors on either end, sort of encoding the rules here. And if you look closely, the vertex color is actually the sum of all the edge colors that come into that vertex. So we have a nice geometric way, or graph theoretic way to think about this and represent the rules of this game. And then using this idea, I thought about a related game you could play with dominoes. So we can apply that to dominoes if we have the right kinds of things. And so I constructed some that look like this. So instead of having pips, they have squares of color on the end. And the play on the left sort of makes sense. The green goes with the green. In the middle, the green sort of square end can match up against the blue, yellow, long edge of the domino, because that some of blue and yellow is green. And then on the right, we have red plus white is green, because white has the 3 primary colors in it. We turn the red switch back off. We're left with blue and yellow, which makes green. So this becomes a set of double 8 dominoes with which you can play standard domino games. And here's some of my students playing this game at school. And this slide is not loading. There's something there. Oh, there it is. So copy this on cardstock as my exchange gift, and thank you for your time.
System comes up in natural hands often enough that it's a good system. So human beings have come up with many ingenious notations and systems and mathematical analysis of lots of things. Here's Egyptian hieroglyphics, here's Morse code, here's music. Here's music again with choreography thrown in. We can actually record these days choreographic performances even before videotape they did this. Here's shorthand, here's mathematics itself. On the lower right hand, we have a notation for juggling. Let's see, what's this guy's name? The Australian juggler Colin Wright developed a notation for juggling. And he said that because of this notation, they actually discovered tricks that no juggler had ever done before. What if we could do the same thing for bidding that all these other notations have done for other fields? Nobody has done that yet. That's my question and my challenge to the world. Come up with a good notation and a good analysis for bidding that achieves all these conflicting goals. Thank you very much.